little bit of overview of where we're at with things. So this is a live stream that we're trying to do about every week or every 2 weeks with training. It is an exclusive session, meaning we don't allow unlimited access to it. And the reason for that is that I want to keep it small and I want to be able to answer questions at the end of the session. While I'm running the session, feel free to post questions, but I'm not able to really monitor the questions that well while I'm presenting. And what I'll do is I'll get to all the questions at the end of the session. You can post those in the chat, just where I posted the welcome everyone message a few minutes ago. Another thing I wanted to share, I'm currently working on a new class at Stedman SQL School, which is stedman.us/school is the URL for it. And that class is about SQL Server replication. It's something I'm currently working on. It's probably going to be available in about a month. So if you're interested in a SQL Server replication class and you want to be one of the first people to get details on it, shoot me an email to steve@stedmansolutions.com. and we'll get you on the preview list for that SQL Server replication class when it becomes available. Okay, well, let's jump into SQL Server indexing. SQL Server indexing is one of those things, it's a topic that I've covered this year after year after year, and we do a lot of training on it, and it's one of those things that it just keeps coming up over and over again to be able to share some good information on it. And one of the things we do at Stedman Solutions is we have our managed services offering where we will help clients and basically on a retainer or a fixed price for the whole month, and we help them with all their SQL Server needs. Quite often, when somebody calls me up and says, I've got an issue with my SQL Server where there's blocking or there's something that's clogging it up so that all the queries aren't getting through or things are running really slow, oftentimes we start looking at it and we find out, oh, well, somebody changed a table or changed a structure or added a new query that's doing something different, that there was no index to support that. We'll get into the detail on indexes in a second, but the thing with indexing is that it's important for performance, and it doesn't matter what language you're talking to SQL Server in. You could be in C# or Visual Basic or Cold Fusion or Python for that matter. And whatever it is that you're running queries against the database, understanding how indexes work and understanding good indexes can help with your overall performance. So the key to having good indexes is to understand how they work. And I'm going to use the example here of a phone book. And I know it's 2024 and not everyone has a phone book sitting on their counter like we did 20 or 30 years ago, but everyone gets the concept. A phone book is a list of people and a list of their phone numbers. And oftentimes it has some other stuff in there too, like addresses. So when we talk about that, I'm going to use that phone book example as a description of how tables are structured. So first off, the first one I want to talk about is a heap. So a heap is basically a table with no clustered index. You've basically just said create table and you haven't put any clustered index on it at all. I know oftentimes where I'm just throwing together a quick table to test something, it might be a heap. And the thing is that in a heap, it's just a collection of rows. There's no logical linking of ordering or sorting of any of those rows. The rows are organized sort of in a random fashion, mostly kind of as they're inserted. There's no guarantee as to what page they'll be on, and if you do things like deleting rows, you might end up with some data pages or 8K chunks of data that have a lot of holes or a lot of missing pieces in it over time. A heap is probably one of the more inefficient ways to access data in the database. So that's where clustered indexes came along. What a clustered index, well, okay, before we go into clustered index, a heap is like having a phone book where instead of that phone book being organized by name or phone number or something that somebody might want to look it up on, it would be a phone book that was simply ordered by perhaps when people signed up for their phone service. So the people that signed up for phone service 40 or 50 years ago, they might be listed in the very beginning of that heap. The people who just signed up for phone service yesterday or today, they're going to be listed at the very bottom of the heap. As you can see, if you were going to look up phone numbers for someone, that heap structure in the order that they signed up for their phone service may not be the optimal way to go find someone's phone number. And We'll go into detail on how that would work in a minute. But then you take a heap, an unclustered table, and you put a clustered index on it. And with a clustered index, you always tell it what to cluster on. Oftentimes people cluster on an ID or an ever-increasing value, like an integer identity or a big int identity. Or you might cluster on a GUID, a unique identifier. Maybe that's not the best option sometimes, maybe it is. But you could also have like a primary key on your main ID, but then you could cluster on something like last name and first name and middle initial in a way that things were ordered by like a traditional phone book would be. The traditional white pages phone book that you would have got 20 or 30 years ago typically ordered people by last name and then first name and then middle initial. So if you wanted to look up me, Steve Stedman, you would have to find the S section and flip through until you found Stedman and then flip through until you found Steve. The clustered index orders tables that way. It basically orders it based on whatever criteria you gave when you created that clustered index. If you told it to cluster on some ID, the entire table would be sorted by that ID. If you told it to cluster by last name, first name, middle initial, the entire table would be sorted by that clustering structure. So that's useful because if you order the table by one of the things that it most commonly will be searched on, then some of those most common searches that when SQL Server queries the table, you'd be able to get there much faster, much like looking up someone by last name in the phone book. Okay, but then we'll go back to the phone book example, and let's say we've clustered our table by last name and first name and middle initial, like a phone book, and you now want to look someone up by a phone number. Well, the only way you're going to be able to do that is to look through the entire book until you find that phone number. So we add the concept of a non-clustered index. A non-clustered index is an additional structure. So originally the clustered index changes the order of the table itself. The non-clustered index is an additional structure that it's like like at the back of the book, an index where you look things up, where you can use that non-clustered index to search through and find something that's sorted in a different order than your clustering key, and then it jumps back to the original table to look it up. You can only have one clustered index on a table because the clustered index changes the order of the table, and it can only be ordered by one sort. Your non-clustered index, you can have several of those or many of those, or too many in some cases, on your table. And because that's a copy of certain columns that might be sorted, ordered, or filtered in different ways in order to give you different help in finding the data that's in any given table. Finally, we have this concept. It's not really an index type, but it's a concept of a covered index, which is if everything you need for your query happens to be in that non-clustered index, it can query just the non-clustered index in order to return your results without directly accessing the table. And that's something that can be a really big shortcut. All right, moving down the list into some other indexing areas that we're not going to cover here. Index views. Index views is a really useful thing, but we're not covering it in this section. Filtered indexes, not in this section either, and XML indexes. Those are some more advanced topics that I didn't have time to fit into this presentation today. Okay, let's go back to the concept of a heap. This is something, I've done this demo, and I used to do this in person where we would have a printout of, here's your phone book, and it'd be like 40 pages listed by just whatever order people got their phone number in. And in this case, that's an example of a heap. If we wanted to do something like search a heap or an unclustered table in order to find the phone number for David Hamilton, well, if you look at this list, David Hamilton happens to be the top person on the list. But the way select statements work is you're not just looking for the first person, but it's going to return all of the people. So if there were 5 different David Hamiltons or David P. Hamiltons in this list, it would have to scan the entire list. And if that was 40 pages of paper, you'd have to search through 40 pages of paper to find all of the phone numbers for all of the David Hamiltons. Now, that's the equivalent of in SQL Server having to search through 40 data pages, for instance, to find all of those specific users. And that's what's referred to as a full table scan. So now, if we wanted to go through and look up the phone number for Haley L. Butler, well, I'm just glancing here and I don't see Haley on this first page. We'd have to just scan through page after page, just flipping through a list of pages. And that's effectively what SQL Server is doing, is it's flipping through its data pages to find a specific person. Heaps are not the greatest structure. And when you're searching on a heap, they're slow. I've got the picture of the tortoise here showing how slow it might be. You search row by row, and if your table is a heap, the only way that any query can pull anything out of that table, unless you're using a top percentage, is to search the entire table, every row on every page. And that's what's commonly known as a full table scan. Full meaning it's doing the whole thing, and the scan meaning it's going row by row by row through the entire table to find data. And that's got to be the slowest way possible to pull data out of any table in SQL Server. So then we add the idea of a clustered index. It's a clustered index is changing this sorting of the table. So let's say you had this phone list as a heap, and then you applied a clustered index to it. What's going to happen is that entire table is going to get resorted alphabetically, or whatever the sort order is specified by that clustering index. If you were clustering by ID, it would be sorted in one order. If you were clustering by last name, comma, first name, comma, middle initial, it would be clustered alphabetically like your traditional white pages in a phone book. So in this case, with a clustered index, if you went back to the example to find all of the people named David Hamilton, if you've got 40 or 50 pages, or in the case of SQL Server, 40 or 50,000 data pages you have to look through sometimes, you don't have to scan through every one of those. What you can do is, using the index structure, it can go right to the pages that contain Hamilton, comma, David P, and return those people directly. And the example of that would be a select statement like this, where you say select phone number from phone table where the name is Hamilton, comma, David P. In this case, it goes directly there, and that's what's referred to as a clustered index seek. If that table has 1,000 pages in it, instead of scanning all 1,000 pages like a heap or a full table scan would do, it's able to use the index and jump through this B-tree structure to get quickly to the row you need. And oftentimes, if there's not thousands of David Hamiltons in there, it would be 2 to 4 different page reads instead of 1,000 page reads. So significantly faster to do what's called the clustered index seek, because you're only hitting 4 8K chunks of memory rather than 1,000 8K chunks of memory or 10,000 8K chunks of memory, depending on the size. And it might be 4, it might be 3, it might be 5, depending on how big the table is, but it's going to be a very small number compared to doing the full table scan that you do with a heap. Now, let's say you have a clustered index and you want to search on something that's either not in the clustering or that has a wildcard at the beginning of it. So if we searched on phone number from phone table, where the name is like percent or the wildcard TON, comma, David P, that could be Hamilton, that could be Walton, that could be Milton, could be any prefix with that. Think about this as though you were using the white pages in a phone book and how you would go about doing it. Well, you couldn't search alphabetically because Wilton or Milton and Walton and Hamilton all appear in different sections of that phone list. So a query like this will cause what's called a full index scan, which starts at the top and goes all the way through the list to find all of the values that would match that. Now, if the wildcard was on the end and you were searching for like Hamilton, comma, D wildcard instead of David, it could get there quickly just like the original one could, because it has the details it needs to go through that clustered index and find it. Now, let's say all you've got is the clustered index and we want to search on just one name. If you have the clustered index on name and you're trying to search on something that's not in that clustered index, like give me all the people who are age 32, well, that's going to require a full index scan because that age is not included in that clustering index. And that's where we introduce the idea of non-clustered indexes. Typically, in a well-designed database, you're going to see tables that have a clustered index, and those same tables also have a couple of non-clustered indexes on them. Typically, a table that's not clustered 99% of the time is a clue that somebody forgot something. Occasionally, there's a legitimate reason, but it's pretty rare. If we have a clustered table where it's sorted alphabetically based off of last name, comma, first name, middle initial, and a non-clustered index that's sorted by phone number, that gives us more power when we're searching to be able to find things quickly. So if we wanted to find all of the names with a phone number of 555-0112, well, for that case, if all we had was a clustered index, we'd have to scan through all of the rows in that clustered index to find that. But because we have a non-clustered index, which has all the phone numbers in sorted order, we could search right to 555-0112. Typically, that's going to be a couple of page reads, depending on how big it is, maybe 5 to 6 page reads at the most. And then it's going to have a pointer back to the clustered index to look up the rest of the row. So it would jump there and then jump right to the page in the clustered index to pull the row back. So it uses the non-clustered index to figure out where the row is, and then it goes to that row in the clustered index to look it up. So instead of scanning 1,000 pages, which you would have to do to do a phone number lookup, if there were 1,000 pages in the table, you're able to do it with just a couple of reads, probably less than 10, depending on the size here, probably 4 or 5. Much quicker to go and look up data with that non-clustered index. So if we do that search that I just talked about, where we're searching by a phone number, it's going to do 2 different operators. First, it's going to do a non-clustered index seek to find out what rows in the clustered index it's on, and then it's going to do an index seek on the clustered index to go and find that row lookup. And combined, that's probably going to be 4 to 10 different reads to do all of that, depending on the size of your table, compared to thousands of page reads if you didn't have those indexes there, or if it was just a heap. There's the concept of a covering index. And the covering index is kind of cool. And I've added a few of these for reporting purposes, where you've got a report that's really slow and you realize if I created a non-clustered index that had a couple extra columns in it, that I would be able to get those reports to run a lot quicker. With the covering index, it's still just a clustered index or a non-clustered index, but the covering index is a non-clustered index that happens to include everything that you need in order to service that query. So if you said select star from this table where the phone number equals something, well, that's probably going to have to go to the clustered index to look up the star, meaning looking up everything in the row. But if you're saying, giving me just the name I'm looking for from that phone number, if the non-clustered index on phone number and name, as shown down below here in the green, if that's available, you're able to go and look up based off the phone number, return the name, and do that with just a single index seek, rather than having to do a full scan to get there. So a quick summary on this, and then we'll go into the demo of how to find out a little bit more of what's going on with your database with these different index types in Database Health Monitor. So first off, we talked about a heap. A heap is basically a non-clustered table or a bunch of 8K pages that contain rows of data in who knows what order. Could be the order they were inserted in, or maybe rearranged over time. We talked about a clustered index. A clustered index is a way of taking that heap or that random ordering of data and sorting it in a specific value that you're going to commonly search on or commonly look up on. And then we talked about non-clustered indexes. Non-clustered index is a copy of some of the columns into a different structure that's used to look up data, and then jump back to the clustered index to get the data. And then there's a covering index, which covers, it's where everything you need to return the query is in the non-clustered index, and it never even has to hit the table itself or the clustered index itself. Actually, a couple more slides before we get into the demo, because some of these apply to the demo. So there's the concept of index waste. The thing with SQL Server is that tables are usually your biggest thing in the database. And with those tables, you end up with big indexes as well. As your database gets bigger and bigger, and your tables get bigger and bigger, so do your indexes. And if you've got really big tables and you have 2 indexes on the exact same columns, that's a complete waste, because you're basically, it's like at the back of the book having 2 indexes that are sorting by the same value. Well, you really only need one of them, because 2 of them aren't going to help in any way. But with duplicate indexes, there's a concept of an exact duplicate versus a partial duplicate. And an exact duplicate means that if the index has 5 columns in it and its duplicate also has 5 columns, then they're an exact. A partial duplicate is where if one index has 5 columns and the other index has the first 3 columns, that's considered a partial duplicate, because that other index could help or could do the same thing. The bigger index could do it all, maybe not always as fast as the smaller index could. So excessive duplicate indexes can slow down your insert and updates with really no added value, because every time you're inserting, updating, or deleting a row, your clustered index has to get updated, but so do all of the other non-clustered indexes on the table. So if you have 5 duplicated indexes, that's 5 times the work as one single index doing that with no added value at all. And the thing is, if you have excessive duplicate indexes, each one of those indexes gives the query optimizer more choices on how it's going to go analyze data. But if you have duplicate indexes, you're giving the query optimizer different choices that really mean the same thing, and it may slow down the query optimizer on how long it takes to figure out the plan of how your query is going to be run. So duplicate indexes can be trouble. That's one of the things we're going to look for, and we can talk about and find ways to clean those up. There's also the concept of unused indexes. And unused indexes are indexes that maybe somebody created and they added a number of columns to them and they aren't needed. They aren't being used. And why aren't they being used? Well, they might have been indexing on columns that are obsolete, or maybe there's a better index that was added or a duplicate index that's being used instead. So imagine if you went to the trouble to build a bunch of indexes and chewed up a bunch of disk space with them, and then they never got used. That's what unused indexes are, and they're completely worthless, and they're slowing down inserts, updates, and deletes. Now, when we talk about unused indexes, we want to make sure they really are truly unused, because sometimes there might be an index that's put on a table that's only used once a month for some month-end reporting, or that's only used annually for some kind of annual reporting, and it's vitally important, but if you took it away, that end of the month reporting to be used. So when you're looking at unused indexes, you really want to make sure they are truly unused and that they're not being used by some process. Maybe they're totally unused this week, but next week, if it's the end of the month, they might be needed. So that's one thing. When you look at unused indexes, you want to study them over time to see over what time period they're actually not being used. Example of duplicate indexes and some of the waste associated with this. Here's a sample. The table's called people, and in the people, we're just going to pretend there's a dozen columns. And one index contains column 1 and column 2. Another index just contains column 1, and a third index contains column 1, column 2, and column 3. Well, technically, if you just got rid of index 1 and index 2 on this, and we're talking non-clustered indexes in this example, index number 3 could do all the same work that index 1 and index 2 would do. But it's not quite that simple. You've got to analyze it and understand it, because let's say column 3 was some gigantic column, varchar 4000, that was just full of data. Well, that might mean that index 3 is really huge and there's a whole lot more searching that it has to go to find your data. Whereas if index 2 was available or index 1 was available for certain queries, it might run a lot faster. So when you're looking at duplicate indexes, you want to understand, are they truly an exact duplicate or are they a partial duplicate, as we've shown here on this slide. So we'll take a look at index waste in a real-world example here. This was a place that I worked at prior to starting Stedman Solutions. So this was more than 10 years ago, where real-world example, developer had just learned enough about indexes to be dangerous. And that's the thing. Whenever you learn anything new, you're typically a little bit dangerous until you get a complete understanding of that. And that's what I'm trying to help here with this demo. So the developer thought, oh, if I just create a script that can scan the entire database and create indexes on everything that might be a foreign key or might be a likely column that was going to be queried. And he added, I don't remember how many it was, but it was thousands and thousands of indexes to a database that didn't even have thousands of tables. And it easily doubled and possibly might have tripled the database size just by adding all those indexes. And then, to make it worse, that developer then wrote the middle tier code to scan the database for tables and indexes and generate their accessor code based off of what indexes were available. The problem was that a lot of these indexes weren't even being used. There was no business case for it. Some of them were linking to tables that had foreign keys that weren't being used or that weren't needed anymore. And then, to make it worse, the code generation process then locked the database structure, so that if we were to remove indexes, it would then have broken the middleware code talking to the database, and bad indexes couldn't be removed in that example. The result was this database ended up with many unused indexes, many duplicate indexes, and lots of wasted time, money, and database resources. And that little project that developer built in about a week's worth of time took about 4 years to completely undo and get this database back to a point that it could be used reliably, because there were so many things that had locked into the tentacles of this middleware that prevented it from being able to change the database. Now, I think middleware is a great thing. Generating code in that middleware is a great thing, but forcing the database structure to be based off of the middleware can be very dangerous. Okay, let's jump into Database Health Monitor demo here on how to find some of these indexing issues. Okay, here we have Database Health Monitor, and if you're already using it, you'll get a free 3-month trial just by completing the form that associates your email address with that free 3-month license. And here I'm connected to, about 20 different SQL servers. And because I have the unlimited license, I'm able to connect to as many as I want. The server we're going to be looking at is this server called Steve Laptop /SQL 2022, which is what I have running here on this computer that we're doing the demo from right now. So with that, we have a list of all of the databases on this SQL server, and there's 3 databases that we're going to be looking at. We're going to be looking at one called Index Test, we're going to be looking at one called Lots of Indexes, and we're going to be looking at another database called Sample Bad Database. Now, hopefully you don't name your databases like this, but these are all demos that I'm using to kind of show different indexing problems that we run into, and I use them frequently when we're testing Database Health Monitor for different things. So if we take a look at this Index Test database, we're going to scroll to the real-time section and then into the indexing section. And in here, the top index report, not a lot there right now because this isn't a very big database, but we're going to hit the Enterprise Index Review report. And let me just make sure that showed up right. Yep, there it is. So what this does is it goes out and scans this entire database, which isn't very big in this case, and it comes back and shows the tables that have missing indexes that could save you the highest cost on your system. So in this, there's a table called departments, and in here there's an ID, department, parent, and so forth. And here's the red flag. The table has no indexes on it. And this report is suggesting an index with a cost of $223,000 there. And these cost numbers come from when you look at an execution plan, how much value is actually associated with different operators in the execution plan. And there's no dollar to cost to exact equation there. It's just a relative thing. So this one at $223,000 is slightly more valuable than this other one at $222,000 to add. And if you could only add one of them, you might take the higher cost one. So in this case, given that this table has no indexes, one of the first things I'm going to look at is, should we add a clustered index to this table before we add any of these other indexes? I'm going to consider adding that clustered index, and then we look at, once it's been clustered, should we be adding these other indexes here? And a lot of the times I'll look at this, grab the index, apply it and test it, and see how things perform before and after adding that index. And we scroll through here. Yeah, this first table, it looks like it's recommending 4 indexes. I would not start by adding all 4 of them. I would start by adding the ones with the biggest value and seeing how things go. Because, for instance, if we added these that are showing here, we added one with item count and parent, and another one with just item count, and another one with just parent, we could end up with partial duplicate indexes that don't really add value. So I would try adding them one at a time and kind of analyzing and see which one would give you the best value in a test environment, and then put it on production. Another table called Even More Departments. Again, no indexes on this. Keep in mind, this is my index demo database, and it is set up to have problems. And that's what we're finding here. So this report, it's just showing 2 tables because it's a small database, but if you run the same report on your actual production or dev environment, you'll be able to see what are the biggest missing indexes that could be applied to that entire database since SQL Server was last restarted, or since. Okay, so that's an incredibly valuable report. The tendency if somebody looks at this is to go and say, oh, gee, this report has 80 indexes. Let's go add all of them. Don't do that. Don't ever do that. What I'm going to look at is figure out, okay, what are maybe the top 10 of the most valuable index out of all those 80? Consider adding those, see how the system performs, let it run for a little while, maybe a day or two, and then come back and look at this report again and see how it changes. Again, you get that by going to any specific database, drilling down on the real-time section, and then indexing, and then from there, the enterprise index report. This database didn't have anything missing, so that's a good state. Okay, next we're going to take a look at these other reports that we have available under indexing. We have the big clustered index. This database does not have any clustered indexes, so it doesn't find any. Let's go to this other one and see if there's any there for the demo. And the problem with big clustered indexes is that, and again, this database doesn't have any either, so we'll go look at this one other bad database. And whatever value is in your clustered index also gets copied into your non-clustered index. So in this table, we have it's clustered on some data that's a 16 and more data that's 8,000. We'd want to go look at it. But that ends up being a really wide clustered index. And your clustered index, you don't want to be that wide. And that can really add to a lot of performance issues because it gets copied into every single row of all of your non-clustered indexes. So big clustered indexes is one of those things that if you've got a lot of them like this one, you may want to consider putting a different clustering key on it. Taking a look at other reports here under indexing, we're going to take a look at the duplicate index report. This database is good. It doesn't have any duplicates. We look at this other database on the duplicate index report. And this is where this one might be a little bit silly because I wrote a script that just went and ran and added hundreds and hundreds of duplicate indexes. In a real production environment, oftentimes I'll run this report and see, yeah, there's some tables that have 4 or 5 or even a dozen duplicate indexes on it. And what we can do when we're looking at this is we can double click on one of these rows and see that table number 29 has 49 duplicate indexes. And when we double click on that, that pops up with our duplicate index advisor, which is showing us that there's 7.5 megabytes of waste, which isn't very big. I mean, which is quite a bit because this is such a small table. Each of these indexes is 156K, and they're all indexed on column C1. So what you'd want to do is go and look at, well, what reason could you possibly have to have this many duplicate indexes? And there really is no logical reason that anybody would have that many. And you could go and create a script to drop it. And you can copy and paste this into Management Studio, review it, make sure it's doing the right thing, and you can drop those excess duplicate indexes. Now, one of the things that there is a legit reason to have duplicate indexes sometimes is if you have an index and then it happens to also have a unique constraint index put on it, that unique column would be true. So you want to be careful that you don't go and delete a unique index. That would be one case that a duplicate might be a valid reason for having a duplicate. Duplicate indexes are bad because they confuse the query optimizer, or not confuse it, but they take more time to process it. They add extra work when your index and statistics maintenance is going on, and they take up more space, bloating your backups and slowing down your backup and recovery time. So overall, plus they're slowing down inserts, updates, and deletes because all of these 48 duplicate indexes on this one table all have to be updated every time there's a row being inserted, updated, or deleted there. Next, we'll take a look at our index fragmentation report. I might not have a database that has enough fragmentation here because it's a demo purpose to actually show this one very well. We'll let it run for a minute and see if we get anything. And I'm pretty sure it's not going to show anything, but it's scanning the database. What it's doing is it's going and it's looking, and for fragmentation, it has to look for tables that are over a certain size threshold. Because if you have a really small table that's fragmented, it's not that big a deal because it doesn't add that much space. But this is going and looking at all the tables in this database and trying to figure out, and all the indexes, and trying to figure out if any of them are fragmented enough to recommending defragmenting them. In this case, well, we'll let it finish here, but this is our duplicate index in one, and there's a bunch of indexes here. Generally what it would do is it would show you a chart showing the most fragmented indexes on your biggest table, and you could then go create a script to go and reorganize or rebuild them all. Keeping in mind that a rebuild operation takes the index offline unless you have SQL Server Enterprise Edition, and the reorganize will allow you to restructure that index without causing it a complete rebuild. And there are quite a, oh, and this is a pretty slow database on my little laptop here. So hopefully this will finish soon. There we go. So it's basically saying there's a bunch of these that are at 50% fragmentation. Well, they're all just copies of the same thing, so they're all the same size. But if we create a script to reorganize them all, we can do that in order to generate, copy and paste that into SQL Server Management Studio and run it. The next one we want to look at is our inefficient indexes. And what inefficient indexes means is that we have indexes that have a lot of updates, but that may not have so many lookups, scans, or seeks. In an optimal world, you're going to have more seeks, scans, and lookups on your indexes than you do updates. Meaning, if the updates is greater than the number of seeks, scans, and lookups, that's telling you it's way more work to maintain this index than it is for what it actually uses when it's being run. With this, we're looking for, in this example, there's 3 shown here where one of these indexes has 0 seek, 1 scan, and 1 lookup. I would want to go look at that index and see what is it being used for, and with just 1 scan or 1 lookup, or just 1 scan and no lookups and no seeks, is that something that we could consider just dropping or getting rid of? Next, we have the missing indexes report, which is just another way of looking at that same report we looked at earlier, showing you here's the cost and some of the missing indexes. And when we click on that, it brings up and just shows us the script that we can use to go and create each one of those indexes that may be missing. Following that, we have most used indexes. Do we have an, yep, so here, this one is showing the ones with the most seeks, scans, and lookups. So these are the indexes that if you're looking at duplicates or looking at those that aren't being used, these are the ones that you wouldn't want to touch. These are the ones that are giving you the most value that you wouldn't want to get rid of. And then we have another report on unclustered tables. And an unclustered table is basically a heap. So every one of these tables, based off the number of rows sorted here, is a table that is a heap that could get a performance boost out of it simply by adding a clustering index to that table, clustering on the right value, something that's frequently queried against or joined against and unique. Then we have the unused indexes report. Let's see if we have that an example here. Okay, well, the unused in these 3 test databases, I don't have an unused one showing up, because they've all been recently built, updated, and changed as part of my demo that I put together. But that's basically the overview of the indexing reports that are part of Database Health Monitor. Each database, you want to focus on the different reportings. The Enterprise Index Review Report is what we looked at to show those things that were missing. And then it just kind of gives you an overview of all the different aspects of what's going on with indexes in your database. I'm going to ask if there's any questions, and I'm going to flip over to the YouTube questions. And Tom put in a question or a statement, my analogy for a heap, which I think is somewhat correct, and I like this one as he describes it. It's like a fish in an aquarium, and the fish are all at random locations. Yes, that's a great description, and absolutely I may use that in the future, describing that at any point in time, depending on different operations, things could be changing around as to what's actually in that heap location, just like fish swimming around in an aquarium. I like that. Thanks, Tom. Question from Charlie, or statement. Let's see. Great stuff as always, and sorry I may have missed this. I was a bit late. Are most of these reports done per database? Okay, and there's a couple other questions, so we'll answer that one first. Yes, the reports, all of the reports that I showed you today are done on a per database basis. Because generally when you're dealing with indexing, it's something that's contained inside of a database there. So yeah, all the reports I showed today in Database Health Monitor, first you drill down to the database, then you drill down to indexing, and then the report is there. Is there a way in database health instead to get such reports across all databases? That's a great question. I don't have that right now, but now that I've actually got a couple different developers working on Database Health Monitor with me, maybe that's something we could consider adding in as a new feature. Yeah, sometimes it would make sense. There is one way we have using the SQL Performance Monitor, which is a thing I built where you, in Database Health Monitor, you right-click on a database, you go to SQL Performance Monitor, and instead of showing you indexes on a specific database, it'll show them across the entire system what databases are missing right now since you started running that monitor. So the SQL Performance Monitor, which I don't have all set up and ready to demo on this day, would be something you look at, and you basically get to that by right-clicking on a SQL server in Database Health Monitor and choosing the SQL Performance Monitor. It'll load it up and give you the queries that are missing right now at this point in time, rather than those that have been missing since SQL Server was last restarted, like what the other report showed. Okay, any other questions at this point?
Thanks for watching our video. I'm Steve, and I hope you've enjoyed this. Please click the thumbs up if you liked it, and if you want more information, more videos like this, click the subscribe button and hit the bell icon so that you can get notified of future videos that we create.